Alright, let's start a new chapter 17 on differentiation. First thing, let's define, review the rate of change. So for a straight line, the when you define the gradient, which is the rise of a run, it also will define the rate of change between 2 points. So for example, on that graph between P and Q1, the average rate of change is just the gradient between those 2 points. As this point Q1 moves closer to P, we get Q2, Q3, and eventually Qn. As n increases and gets closer to P, that line is called the tangent, and the gradient of that line will be called the instantaneous rate of change. Okay, now to determine the tangent to a curve at a point, let's look at a simple function, which is y equals x squared. If we define a point on that curve, but let's fix its x coordinate to a value a. The y coordinate is a squared, coming from the rule of the curve. And let's place another point Q further away from P, but not too far. And the way we define how far it is by adding another parameter that we're going to call h. H is going to be really small. So a plus h is the x coordinate. So the difference from here, if I just annotate, it's going to be done later anyway. We have a plus h as the x coordinate. Again, it's on the curve, so it follows the same rule. The y coordinate is going to be a plus h squared. Now from P to Q, let's determine the rate of change. So we do use the gradient rule, which is the rise of a run. On the numerator, we write the difference of the y coordinates, and on the denominator it's the run, or the difference of the x coordinates. By simplifying, we get 2a plus h, and we're going to introduce the notion of limit. So we have 2a plus h. They both are sort of parameters or variables, but if we focus just on h, and we're going to set as h approaches 0, that expression will become close to 2a. So the gradient of the tangent at P is said to be 2a, as it is coming from that limit. So the straight line that passes through the point P has a gradient of 2a, and is called the tangent to the curve at P. Now we say that the derivative of x squared with respect to x is defined as 2x. Or we can say that the derivative of x squared is 2x. Now we'll elaborate how we get to that statement about the derivative, which is a definition, but how do we get the 2x? It's coming from the 2a before, and we'll go through looking at the way we worded it. Is we determine the gradient, and it's a method called using the first principles, and then we'll move on to determining the limit and then the derivative. Okay, so let's apply that by changing the rule slightly. A set point with a given value. So the rule is y equals x squared minus 2x. We had a given point of coordinates 3, 3. So the x equals 3, The y is calculated by substituting the x value, and that will be on the curve. And then we have a point Q further away from the x coordinate of P by an amount h. The y coordinate is determining by substituting x by 3 plus h. And then to determine the gradient from P to Q, we do the rise over run. Here is the rise over run. The run simplifies to h. For the rise, we need to expand the brackets and regroup the like terms, and that gives us 4h plus h squared. Now, because h is different from 0, we can simplify, and that gives us 4 plus h. We'll introduce the concept of limits. We set h approaches 0, therefore the gradient will be just 4 because that value becomes 0. Okay, next example. Different rule. This time the point P is an x variable, so we don't have 3 like before, but we use the same technique by determining the rise over run, the gradient between P and Q, and then we're gonna make change that expression as h approaches 0. So here's the gradient. There's a little bit of algebraic manipulation. You expand the brackets, regroup the like terms, and then we simplify by h. That gives us an expression without a denominator, which is 2x plus 1 plus h. As h approaches 0, that gradient becomes 2x plus 1, and that's the definition of the derivative. Now, instead of saying as h approaches 0, then the limit of that expression becomes 2x plus 1, what we do is write lim for limit of the expression, and the as h approaches 0 is that h with an arrow towards 0. So to find the derivative of that function, first is you determine the gradient between P and Q. P is on the curve, Q will be on the curve but away by a h amount. You simplify that expression, and then you find the limit when h approaches 0. So that's the general technique. Okay, so now we have a cubic. We have a point P here. It tells you what Q is, and what you want to find is the gradient of the tangent at that point P, which is the same. So P 28, and that's 28, that's the same coordinate. Find the gradients, simplify the expression. We get a this expression. Now when h approaches 0, all the h terms become 0, so what's left is 12, which is the answer to the actual question. Alright, here from there, what you should do is pause the video and attempt with pen and paper to find the limits of those 4 questions for you to practice. Okay. Any terms, you're looking at the expression, you scan the expressions, you look for the terms that have h. So let me get a pen. See, when h approaches 0, that has an AH, so that cancels out, that crosses out. What's left is 22x squared, which is fine. There's no more h in it. B, it's a fraction. If h approaches 0, the denominator approaches 0, we can't divide by 0. So before you calculate the limit, you need to simplify your expression So any h terms here crosses out, and you get 3x squared plus 2h. So you don't divide by h anymore, and the 2h here simplifies. What's left is 3x squared. Next one is just for you to practice. The expression 3x has no h, so it's the same, and it's the same for a constant independent of h, so the limit will be exactly the same. Okay, the, the way we're going to rephrase that is, how do we define the derivative? So again, remember, we're looking for the tangent at point P. So we define a Q point, which is further away by h. We determine the gradient between P and Q, or the secant, which is the segment between those two, and that gives us f of x plus h of minus f of x over h. That's your rise, and that's your run. So the gradient of the tangent is defined to be the limit of that expression as h approaches 0. So this is a compact notation. So that's your gradient, and that's the limit when h approaches 0. That's called the derivative, and the notation is f with a little dash here. It's a function of x, as your gradient will change depending on your point along your curve. Also, the tangent line of the graph at the a point, a f of a, is defined to be a line that goes through the same point, and the gradient is f prime of a. Very useful. You need to remember that as you want to determine the equation of that line. Okay. Differentiation by first principles. Nothing new. It's determining the derivative of a function by evaluating the limit, which we've done that before. So here we have a function. What you need to do is, your point P is at x, your point Q is at x plus h. You come up with your gradient, which is that expression. You expand the brackets, regroup the like terms, and try to simplify as much as you can. You get your expression, and then you do a limit when h approaches 0, which gives you 2x plus 2. Therefore, the derivative is 2x plus 2, which is also the gradient of the tangent at a point where the x coordinate is a variable. If you wanted to find it when x equals a, you just substitute the x value here. Alright, last example for you to practice. Pause the video, determine the gradient, do the simplify the expression, and find the limit. Alright, so first, to determine the gradient, set a point P where at x and Q at x plus h. Write your rise over run. So here's your rise. Your run is, you will notice the pattern. The run is always going to simplify down to h. The work is going to be done on the rise. You need to expand that cubic, which is the most of the work that you need to be doing. Regroup the like term and simplify, which we have here, and then divide by h. On the numerator, all the terms have a h factor, and then you apply the limit when h approaches 0, and we get negative 3x squared. And that's it for the first exercise on chapter 17, and I'll see